This question is asked in Gate 22 of Instrumentation. This is from digital subjects and from combinational circuit topic based on the magnitude comparator concept. The question is, A equals to A1 A0, B equals to B1 B0 are 2-bit unsigned binary numbers. If f is a function of A1 A0 B1 B0 is a Boolean function such that f equals to 1 only when A greater than B and f equal to 0 otherwise, then f can be minimized to the form. Okay, so these are the 4 options we have. Then, okay, one of the ways you draw the truth table first, and from there you get the mean terms and again simplify by K-map or Boolean algebra, whatever. Otherwise, if I draw a K-map, from there itself the comparison will be very, very straightforward. You don't have to think anything. Okay, so this side, let me take it is A1 A0. This side, let me take it is B1 B0s. So because it's a 4 variables, I'm going with 4 variable K-map. Okay, so what is the technique actually? So this is A1 A0 value is 0 0, this is 0 1, this is 1 1, this is 1 0, this is 0 0, this is 0 1, this is 1 1, this is 1 0. So I have to always check whether A1 A0 is greater than B1 B0 or not. A is a number, B is a number, whether A greater than B or not. If yes, then this is 1 I should take. If not, I should take it is 0. In the first box, so A1 A0 value is 0 0, this is 0 0. So whether A is greater than B, no, so this is 0. In the entire row, I can say these are all zeros because A value is constantly 0, B value is 0, 1, 3, 2. I mean, if you find in the decimal form, A is 0, this is 1, this is 3, this is 2, B is 0, 1, 3 and 2. Because in the first row, A value is 0 and B value is 0, 1, 3, 2. So of course, A is less than B in all 4 cases. So that's why it is 0. In the second row, if you see, I mean this row, the first box of the second row is A value is 1 and B value is 0. So yes, A is greater than B. So you get here 1. Next case, A is 1 and B is 1, 3, 2. So again, A greater than B we are not getting in the remaining 3 boxes. So I'll get here zeros. Next row, if I see, A value is 3. I mean this row if I see. So if I see the third row, okay, A value is 3, B value is 0 in the first box, so you get 0. A value is 3, so 3 is greater than 0, you get 1. 3 is greater than 1, you get how much? 1. 3 equals to 3, you get 0. 3 is greater than 2, you get here it is 1. Similarly, in the last row, A value is 2, and in the first box, 2 is greater than 0, you get 1. 2 is greater than 1, you get 1. 2 is less than 3, you get 0. 2 equals to 2, you get 0. So this is what is the corresponding K-map is. Okay. So like very well in the 2-bit magnitude comparator, there are 6 combinations where A is greater than B, 6 combinations where A is less than B, and 4 combinations where A equals to B. And here you can see there are 6 number of ones we are getting as expected. So now, like we can have the grouping. So you can see a quad is possible here. And to club this one, this is the only way. And to club this one, this and this. So if I ask you what is the expression for this one, okay. So from row, what do you get? From row, you get A1. And from column, in the first 2 column, if you see, you get this is B1 bar. And from this one, from row, you get it is A1 A0 because it is constant, and from the first and the last column 0, that is your B0 bar, A1 A0 B0 bar. And for this particular pair, what do you get? From row you get A0, and from column you get it is B1 bar B0 bar. If you check it, if I write it, so F is basically A1 B1 bar, I mean this term, plus then this term if I see A1 A0 B0 bar, then the next term is A0 B0 bar B1 bar. So this is what is the expression of F. And if you see, so this is nothing but is given in option B. So B is the right answer for this question. Okay. So again, it's a simple questions, and in the previous year in 2020 instrumentation also, this model question has been asked. Okay. So just you need to know the functionality of a comparators, and then you can easily have the 4-variable map in a 2-bit comparator case, and you can simplify this. So this is the expression. The answer is option B in this case. This question is asked in Gate 22 of Instrumentation. This is from Digital Electronics topic from the Logic Gate chapter. The question is, the logic block shown has an output F is given by, you see these are the options we have, right? So this is A, this is B. So what is this F in terms of A and B? So let us try to simplify this. If this is B, so this means this is your B bar and this is also B bar. Okay. And if this is A, this is your A bar. And if this is A, this is your A, right? So wherever the dots are there, so I'm just highlighting them. This is your A bar, this is your A, this is your B bar, and this is your B bar. So if I ask you what is this output, this is a NOR gates. So this output will be A bar plus B bar, NOR of this, right? I mean A bar and B bar should be NORed. So it's basically A bar plus B bar whole bar. So this happens to be by De Morgan's law. If you try to simplify this, so this is your AB. Similarly, what is this if I ask you? This is your A plus B bar whole complement. So, and if you simplify this, this happens to be A bar B. And what is F if I ask you? This F is basically again NOR combination of this and this. So F is equals to AB plus A bar B. This is whole complements. So whole complement, if I take B as common, so this is your A plus A bar. So this is basically B bar, because A plus A bar is 1 added with B is B, and over this is basically B complements. So if you see, this is given option D. So D is the right answer for this question. This question is asked in Gate 22 of Instrumentation. This is from digital subjects and from combination circuit topic related to the multiplexes. The question is, the output F of the digital circuit shown can be written in the forms. Okay. So from the framing itself, it is clear like this might be a MSQ questions. Okay. So let us first try to get the expression, and then we'll see which options will satisfy this F expression. Okay. So coming to, if I ask you what is your Y, so Y, this is basically this outputs. This is basically B bar I naught plus B I1. So this is B bar. What is I naught? I naught is 1. And what is I1? I1 is 0. So this is B dot 0. So this is basically B bar, or is 0. This is basically B bar. So Y we got, this is B bar. Similarly, if I ask you what is F, so F, if you see the select line is A here. So this is your A bar I naught plus this is A I1. So this is A bar added with 1 plus A with I1. What is I1? I1 is Y. So this is basically B bar. So if you see, this is A bar plus AB bar. So this can be written as A bar plus A added with A bar plus B bar. So that happens to be A bar plus B bar. A bar plus B bar can be written as it is AB whole complements. By De Morgan's law, if you split AB whole bar, so that happens to be A bar plus B bar. If you see, A bar plus B bar is given in option B, and AB bar is given in the option A. So basically, this is indicating a NAND gate, 2-input NAND gates. What about option C? Option C is not correct because this is NOR gate. A NAND gate can never be equals to NOR gates. Similarly, A bar, B bar is basically again the NOR gate. So this is also not true. So if you see, option A and B are correct for this. This question is asked in Gate 22 of Instrumentation. This is from digital subjects and from the data converter topic. The question is, an analog to digital converter with resolution 0.01 volts converts analog signals between 0 to 10 volts to an unsigned binary output. The minimum number of bits in integer in the output is dash. So basically, resolution is given, a resolution having a well-defined formula in terms of bit size. And by equating that equations, we can easily get the value of n, the number of bits. So, you know, like the resolution is of a ADC is given by, okay, V max minus V mean divided by 2 raised to power n. This is a analog to digital converters. That means, you know, like this is what your analog inputs, V in, and digital output. So how many binary outputs will be there? That depends on the resolutions. So we need to find how many such lines are there. So resolution is given by V max minus V in divided 2 power n. So anyway, in this case, you know, resolution is given point how much? 0.01, right? So you see the resolution. And Vmax minus Vmin, that means what is the range of this input voltage? So that is your Vmax is 10 volts minus Vmin is 0 divided by 2 power n. So if you simplify this, so 2 raised to power n happens to be 10 divided by 0.01, or basically 2 raised to power n happens to be 10 by, so this will be how much? This will be 1000. Okay. So I mean, of course, no integer value of n can satisfy this, but we know 2 raised to power 10 is 1024, right? And 2 raised to power 9 is how much? This is 512. So 9 bit will not be sufficient to indicate this 1000. So the minimum next integers after 9 is basically 10. So the minimum number of bits that we need is basically 10. 9 will not be enough, because 9 bit means we can go up to 512, but we need up to 1000. So that's why we should be going up to 10 bits. So the answer is 10 for this. This question is asked in gate 22 of instrumentation. This is from digital subjects from the data converter topics. But the question is somewhat inclined to the network subject as well. The question is, a register ladder digital to analog converter receives a digital input that results in the circuit having the state as shown in the figure. For this digital input, the Thevenin voltage VTH and the Thevenin resistance RTH as seen at the output node are dashed. So these are the options we have. So basically we have to observe the states of the switch, okay, because the term which is given, it receives a digital input that results in the circuit having state as shown in the figure. It means because of the digital input, corresponding digital input, the switches are in these corresponding positions, right? So that is what is the first point. So I'd like to first redraw the circuits, by eliminating the switches, because the switch is either connected to 4 volts or it is connected to ground. So taking that into considerations, if I draw, so this 2 kilo ohm resistor I am putting in the leftmost arm. So this is connected to ground. Then I have again one more 2 kilo ohm resistor. But here this is connected to switch A. So switch A, if you see, this is connected to ground. So this is also connected to ground. So I have taken this and I have taken this. Then I have a 1 kilo ohm resistor. Okay. And then I have a 2 kilo ohm resistor, and 2 kilo ohm resistor is connected to 4 volts. If you see, so this arm is connected to 4 volts. So here, so this is a 4 volt supply. So this is again your 2K. So I have taken this into consideration, and this also. Next, I have again one more 1K. Okay, and I mean this is done. Then I have 2 kilo ohm resistor. This is also connected to ground. So I have one more 2 kilo ohm resistor. So this is also connected to ground. So this is what is my output terminal. Okay, so we are supposed to give the value of VTH and RTH from where? From the output nodes. So we are supposed to give the value of VTH and RTH from the output node. So basically, we are supposed to get the value of VTH and RTH, so from this particular terminal. So if I redraw the circuit again, how does the circuit will look like? This circuit will be looking something like this. So you have, so let me do one thing. This 2 kilo ohm and 2 kilo ohm, these are in parallel. So this I am replacing it by a single resistor whose value is 1 kilo ohms. So this is 1 kilo ohms. And this 1 kilo ohm is again series with this 1 kilo ohm as well. So let me do one thing. So this entire segments, so this I am replacing by a 2 kilo ohm resistor. So here I have a 2 kilo ohm resistor. So this is 2 kilo ohm resistor. Then after this we have a 2 kilo ohm resistor here, and then I have a 4 volt battery. Okay, I mean this is also over. Next I have one more 1 kilo ohm resistor, and then I have a 2 kilo ohm resistor. So this is your 2 kilo ohm resistor. So this is what is the circuits. So this is what we need VTH, and to compute RTH also we'll see from here. So how do you get VTH? Okay, there are multiple ways like how do you get VTH. So let me do one thing. So let me take this node voltage is Vx. If this node voltage Vx, then VTH is equals to, by voltage division rule, if I take this point is ground, okay, so this Vx will be divided across 1 kilo ohm and 2 kilo ohm. So VTH is equals to 2 by 1 plus 2 into Vx. So basically VTH is equals to 2 by 3 into Vx. So getting the value of Vx is not a challenging task. So if I write the nodal equations at this node, so Vx by 2 for this segments plus Vx minus 4 by 2 for this segments plus Vx by 3 for this and this segments is equals to 0. So this is a single equation in terms of Vx. Let us multiply 6 both sides. So if I multiply 6, so this happens to be 3Vx, this happens to be 3Vx minus 12, and this happens to be 2Vx is equals to 0. So 336 plus 2 is 8Vx. 8Vx is equals to 12. So Vx is equals to 12 by 8. So this becomes 3 by 2. Vx is 3 by 2. So VTH is equals to how much? 2 by 3 and Vx is 3 by 2. So if you see, this is cancelled. So basically the value of VTH is equals to, we are getting it is 1 volt. So very simple and straightforward. Now what is the next task? Next task is to get the value of RTH. So from where you will see RTH? From the output node. So from here we will see RTH. You know very well, while computing the value of RTH, so what we do, the independent sources should be killed. That means voltage sources, independent voltage source should be sorted, current source should be open circuited. So in this case we have only one source, so that I have replaced by short circuits. And now if you try to compute the value of RTH, so what do you get? So RTH is equals to, if you see, so this 2 kilo ohm is in parallel with this entire segment. So RTH is equals to 2 parallel with, so this entire segment I can say this is 1 plus 2 parallel with 2. Yes or no? 1 plus 2 parallel with 2. So RTH happens to be 2 parallel with, this is 1 plus 1. So RTH is equals to 2 parallel with 2. So that happens to be 1 kilo ohm. So basically VTH value is 1 volts and RTH value is 1 kilo ohm. So if you check the options, VTH is 1, RTH is 1, that is given in option C. So C is the right answer for this question. Okay, yeah, a little bit lengthy. It is taking around 5 minutes of time, but anyway, but it's a simple questions. The answer is option C for this. This question is asked in gate 22 of instrumentation. This is from digital subjects and from the sequencer circuit topic. The question is, the digital circuit zone, okay, if you see the option, is it divided by 5 counter, is it divided by 7 counter, is it divided by 8 counters, and does not function as a counter due to disjoint cycles of states. So basically, you know, like if you see, in this case, we have the D flip-flop, right? And they're in cascade with the additional hardware NOR gates. So such kind of questions, you know, like very frequent, like we can redraw the circuit as if it is a shift register kind of things. And then by, you know, giving some clock, we can check what is the mod number of this. And from there itself, we can conclude what is the correct answer. So let me draw a simplified diagram of this. So we have 3 flip-flops, so it's a 3-bit counter or register, whatever you can say. Okay, so and if you see, so basically the input to the NOR gate is from Q1 and Q2, right? So this is, let's say, Q0, this is Q1 and this is Q2, and the input to the NOR gate, if you see, this is your Q1 and this is your Q2, and the output of NOR gate is connected to this one, I mean this flip-flop. It's a synchronous case, so this is what your clock. So because no term and condition given, so let us assume the initial state of this circuit is basically 0. So now let's do one thing. So I'm making a table. Okay. So the first column in the table is clock. The next column in the table is inputs. So what is the input basically? Input is basically, this is what I mean by inputs. And this is basically Q1 and Q2 NOR combination. So this is Q1 plus Q2 whole complement. So this is the inputs. And next is the next state. So next state is basically Q0 plus, then you have Q1 plus, and then you have Q2 plus. Okay, so this is what the input is. So first, clock number 0, and we haven't given any input. I have assumed the initial states are all zeros. So now first let us find the NOR combination of this and this. So 0 and 0 if you do NOR, so that happens to be 1. So now I'm giving the first clock. So this 1 is coming here, this 0 will come here, this 0 will come here. Then again if I check 0 and 0, I mean always, so my focus is these two column. 0 and 0, so that input is 1, I'm giving the second clock. So this is 1, this is 1 and this is 0. 1 0, again if I check the status, so this is 1 and this is 0. So 1 0, if you find the NOR of this, so that happens to be 0. So now let me give the third clock. So this is 0, this is 1 and this is also your 1. So I'll be continuing like this till I get the initial state 0 0 0. So now 1 and 1, if you find the NOR of this, that happens to be 0. So let me give the fourth clock. So this is 0, this is 0 and this is 1. And again 0 and 1 if you do, so that is again 0. So I am in the fifth clock. So that is 0. So this is 0 and this is also 0. That means if you see, so if the initial state is 0 0 0, then on fifth clock cycle again I am getting the 0 0 0. That means to get back the initial state again 5 clocks are applied. That means it's a mod 5 counters. And if it is a mod 5 counter, then I can say this will divide the corresponding frequency, clock frequency by 5. So you can say it is a divide by 5 counter, which is given in option A. So A is the right answer for this. So very straightforward and repeated model question in the GATE exam.